Everyone, welcome to the part number 4 of the present discussion, potential due to the system of charges, and with some example point of view. Okay, let's start without wasting time. Potential due to the system of charge. In a part number 3 we seen potential due to the dipole. In a part number 2 we seen potential due to the charge or single charge. Today we go for the system of charge. It means many charges are there. It is not difficult, just a modified higher order potential due to the system of charge. Okay, so this is considering now onwards not one charge, two charge. We have a n number of charge, q1, q2, q3, and they are the distances at the r1, r2, r3, as you can able to see in the figure. Okay, so this is our observation point P. From that, this charge is far apart, r1 distance, r2, r3, rn, up to so on. Potential in the versus system which is far from the distance of r1, so v1 is equal to 1 upon 4 pi epsilon 0 q1 upon r1. So it will be, where is q2? It is here, so which is far at the distance of r2, so v2 will be 1 q2 upon 4 pi epsilon 0 r2p. Then v3, v4 and vn you can able to write as shown in the this slide. Okay, let's go without wasting time. This is what we have. The total potential will be the sum of all potential because they obey the superposition theorem. You may aware about now what it is. The superposition theorem is, if you add them, so the total will be the, suppose the potential due to the one's charge is this much, potential due to this another charge is this much, then the total potential will be the sum of its, it will be the superposition theorem they obeys. So this is what we have. We know the all expressions of v1, v2, v3 up to vn. We take a common out of 1 upon 4 pi epsilon 0. It will be the q1 upon r1 plus q2 upon r2, and then go to the qn upon r1. We are not bothering here to the sign of what kind of charge it has, positive or negative. Once you have in a calculation, you can go with the positive negative sign. So yes, we are seeing in a quantized way, but if we are seeing in a microscopic world, it means there is a continuous charge distribution. There we can't say one individual summation. We can't do. We need to do the integration over the all charge density. So we used one continuous charge density tool. I will mention in a below descriptions that link of the video where I explain the continuous charge distribution through which we can understand what is rho r. There we seen line charge density, volume charge density, surface charge density, lambda, sigma and rho. This rho here I am used. So if we this rho into the small element, so it is rho time delta v, which is nothing but the total charge of the system. Actually, if you go for the revised point of view, the total charge on the system will be the q time delta v. Otherwise, the surface volume charge density rho is equal to delta q upon delta v. This is the what exact expressions of it. When we need to determine the potential due to the small volume element, in small volume element how much charge it has, now integrate over the all volume, total charge will be there. Once you get total charge in this expression, you can able to put into the full expression. You will get the potential of the system, which is expressed as v is equal to 1 upon 4 pi epsilon 0 q by r, where your q is total charge of the system. So ultimate our aim is to find potential. For potential we need to find total charge. For the total charge we take different ways for the finding the total charge of the system. Okay, so suppose we have one sphere, not sphere, shell. What is shell? Shell means I can express, I can give one example of its soap bubble. If you have one bubble, your volleyball, which is hollow inside this inside the ball, so this is the way on which the charges on the surface is there. Okay, now we are trying to find the potential at outside to the shell and inside to this shell. What kind of potential it can be, because we seen electric field of by this particular shell, but here we are trying to find the electric potential outside and inside of the shell. So we know that the uniform charge spherical shell electric field outside to the shell at the distance of r, suppose is the distance of small r, the radius of this spherical shell is capital R, then the potential by the total charge is the q. This is the q is the total charge on the shell. So that potential generate at the distance of r, which is 1 upon 4 pi epsilon 0 q by r, where r is the distance between your observation point to the center of the cell. This is most important condition. R should be greater than equal to the r. If it is equal, then your small r replaced with the capital R. If it is inside, and that we already know, the electric field inside the cell is zero. Why? Because if you imagine the Gaussian surface inside the spherical cell, there is a no enclosed charge. Once the charge is not enclosing, in the reference of Gauss law, their electric field will be zero. The electric field inside the spherical cell is zero, but the potential will be not. This is a MCQ most MP. It will be constant because there will be no need to do work for the replacing the charge. If you don't want to do any work, if you no need to do any work, so the potential will be constant, because the potential is nothing but the how much work you need to do for the bringing the charge from there to here. It means infinite to particular point. Okay, so expressions of the potential at inside the shell will be same as what we have on the surface, which is, so v is equal to 1 upon 4 pi epsilon 0 q by capital R. Your small r you can replaced by the capital R, because on surface will be the capital R, which is radius. Okay, this is what we have with the system of charge. Okay, that is you may go for the any kind of shape and size you can. 2.2, there is a two charge, 3 into 10 to the power minus 8, 2 into 10 to the power minus 8, which are far apart. Both charges are the separated by the 15 centimeter distance. And what we have to find, a point of which point which is lies on line between joining. If you have two charge, you may join them, you may got one line. On that line, anywhere one point is lies, where point is lies, that you want to find, where our potential of the system will be going to be zero. This is question. At what point on the line of joining of two charge is the electric potential will be zero? Take a potential at infinite to be, this is a hint like structure. Okay, so let's understand. We have one charge, 3 into 10 minus 8, 2 to 10 to power minus 8. They are far apart by the distance of 15 centimeter. We imagine one point anywhere in between, which is far from the one of the charge is x distance, then automatically second will be the 15 minus x, obviously. Then start to the further calculation, a point P where our potential will be zero, where our point this is, what x distance x we need to find, where any point on line of joining is our becomes potentially zero. So we need to put potential is zero and we will find x. Okay, reverse process. In earlier it was x is given, it means distance are given and we find in the potential. Here we know the potential should be zero and we need to find x. q1p means q1 to p is x distance, q2 to p is the 15 minus x. If you want to go in meter you can, otherwise you can go with the x distance and 15 minus x centimeter. At the end you will get the answer in terms of centimeter. This is what we have, the potential due to the first charge on the p distance, which is far from the x distance. So this is the q1 upon 4 pi epsilon 0 x r squared. Your r is the x, so the x square, sorry, it is a q charge q1 upon kq by r only, not square. Okay, please forgive me, this square is not there in the potential expression. So this is 3 q1 is 3 into the minus 8 4 pi epsilon 0, and this is your r. I am taking in terms of meter, but at the end we will converting into the centimeter again. q2, it will again the charge is 2 into the minus 8 4 pi epsilon 0, and then distance is the r in terms of where it x. So here we have 15 minus x. It's obey the superposition theorem. The total potential on p point v will be the q1p plus q2p should be equal to 0 we want. Then v is equal to 0 we put any intentionally, then 1 upon 4 pi epsilon 0. This is what same exactly what I express and few before slides. Okay, 3 into 10 to the power minus 8 and the x upon 2 10 to the power minus x. This is because of this minus, this is minus 2 into 10 to the power minus x, 15 minus x 10 to the power minus 2. Here we are ignoring the power because see, the 4 pi epsilon 0 is multiplied with the 0, it will be 0. Then 10 to the power 8 10 to the power minus 2, it reduces to 10 to the power minus 6 on both steps. So it will be common out from the outside to the square bracket. 10 to the power minus 6, 10 to the power minus 6 goes to this side, 10 to the power minus power 6 plus 6, but it will be the 0 divided by something, it will be 0. So the only the this term will be reduces. So here we are ignoring the 10 to the power minus 2 time 2, still it will be answer will be in terms of centimeter. That is acceptable. You can see 3 by x, what we get, other all the terms are 0. See, it is all are 0, so this term will be the 0 that I write here. 3 by x minus 2 by 15 minus x is 0. If you reduce this, you will get x is equal to 9 centimeter. This is a one case. If suppose it is a our point p point will be the in between the two charge, suppose it will be the outside to the two charge because it's the on line of joining. Okay, so it is valid case, but it's not in between two charge. Then the distance from the first charge will be the x, then the second charge will be total x minus 15. It obvious because total is x, then the 15 is cancel out, so it will be the x minus 15. Then our expression will be directly 3 by x, 2 reduces minus 2 by, it will be the 15 minus x. Now we have x minus 15. So again same the mathematics step, if you follow, you will get x is equal to 45 centimeter. So we get 2 point on line of joining of x is equal to 9 centimeter and x is equal to 45 centimeter, where our potentials are going to be 0. Okay, it's a very easy example we conduct. Thus this is the what conclusion we made. Electric potential is 0 at 9 centimeter and 45 centimeter. Let's go for the next example, the example 2.3. The simplest diagrams are given. The positive charge is there, which is always electric field outward always if it is positive charge, and when we have negative charge is electric potentials or electric field is always outward towards to the negative charge. And additionally there is a some points are given q, p and a, b. What it is, let us see. A task: give the sign of potential difference vp minus vq and vb minus va. Is it positive or negative, that we want to conduct, or what that we need to guess. Okay, so this is for diagram. We will focus first in the vp minus vq. Okay, potential at vp and potential at vq, which one is bigger? If vp is greater than vq, then answer will be positive. Obvious na, vp is greater than this, it means 5 minus 3 with the positive 2 answer. So is it possible, and why you can able to see, how you can conduct, how you can able to say that vp is greater? You have to give the justification, you have to give a reason for that. I have one reason. V is inversely proportional to the distance. If the distance from the source to that point will be more, the potential will be less. So the potential of p point will be more because it's the nearer to this charge, it is near to the charge, and the potential of the q point will be the less than the p point because it's the far than the p point. That's why the vp is greater than vq. Then obvious you can take a subtraction will be the positive. This is answer of this question. What about vb minus va? Vb minus va, same expression. Vb is far, so it will be less potential. Va is more, so the more number is backside and it is negative sign. Obviously this subtraction will be negative, and this is what oh, positive is given. This is the error. Vb is less, vb is less negative than va, then vb minus va. So vb is less na, and minus va potential is more, so obviously it will be the negative number. This answer should be negative. Error in textbook, this will be negative. Okay, let's go for the B task. Give the sign of potential energy difference of the small negative charge between the point Q and P and A and B. A and B. Okay, let's go for the first Q and P. There in between one negative charge is there, small negative charge there. Let us read the what answer it will be. A small negative charge will be attracting towards positive charge. Suppose we have any charges, negative charges here, but it in the within the center of the positive charge. That's why they are the two different kind of charges are always attract each other, so it will be attract. Suppose you have one charge on P side, suppose you have one another charge on the Q side, both are negative, which will be feel more force to attract to the positive charge. Obvious Vp1 will be attract much faster, or the much stronger force they feel. Okay, the negative charge moves from the higher potential to the lower potential. It means P to center charge. Therefore the sign of potential difference, a small negative charge Q to P will be positive, because Q will be less comes and the P will be plus, so they will be positive. Similarly, potential of A site will be more because it's near to it. Potential of B will be the less compared to A, hence the potential energy difference will be positive, as I said you. Okay, C stars give the sign of work done by the field. By the field, I will explain you in detail. Moving a small positive charge Q to P. Here we have one system, and if our charge reaches Q point to the P point, then how much work done by the field, it means this, and charge will support you or repulsive. This will be decided by the what kind of charge we have here. This charge is positive and obviously center is positive, so what will be the happen? Repulsion will be happen. So when you come from Q point to the near to this source point, which is P site, then obviously repulsion is more, so negative effect will you feel, obviously. So the in moving charge, small positive charge Q point to the P point, work has to be done by an external agency against the electric field. Therefore the work done by the field, which means this man will be applying force on those charge, will be negatively repulsive. Repulsive is negative. Give the sign of work done by external energy. So the here we want to find the work done by external energy, moving from the B point to the A point, and obviously it is negative charge. Okay, one negative charge we have, it is going from the B point to the P point, so it comes nearer, and obviously both are similar charge, negative charge. So this is here negative charge, both are similar charge, it means repulsion is there. So if the repulsion is there, then from externally you need to do more work to bringing B point to the A point. So again, the in the moving same small negative charge from the B point to the A point, the work has to be done on external agency positively. You have to push more. Okay, you need to do more. Otherwise, if they ask a question like work done by external field, then it will be negative, because the field don't want to come to you, because it's a repulsive kind of, they are not like each other. But externally you need to push, because you have to do the more work from the B to A point, A to more nearer point. Obviously it is positive. And the last task, does the kinetic energy of the small negative charge increase or decrease in a going to B point to the A point? If the any charge is going from the B point to the A point, the kinetic energy what will be happen? Because the if it is negative charge, yes, it is mentioned negative charge, so the negative charge will be repulsion. So obviously B point to the A point, when it's trying to reach, obviously repulsion is having, so the velocity of the system will be reduced, and velocity is nothing but the 1 by 2 mv square kinetic energy, so the kinetic energy is reduced. Due to the force of repulsion on the negative charge, velocity is decreased, hence the kinetic energy obviously decreased from the B point to the A point. If this same question, does the kinetic energy of the small positive charge, then this is answer is going to be exactly reversed. Due to the force of attraction of positive charge velocity is increased, hence the kinetic energy is increased from the B point to the A point. Is it understandable? Okay, thank you. Thank you very much for the today's time.